unfortunately, due to unforeseen circumstances, you will not have the pleasure of hearing a talk from a wonderful student and a brilliant mathematician and a rising mathematician. So I'm substitute, second best. What I want to talk to you today is other work of hers that we're doing together, and what I plan or hope to bring to the table, if the nervousness allows me to, is to give a complementary talk to the lectures of Andres Stipsitz, Sabo, Zoltan. Sorry, I'm very nervous, and Inanch by core. So what I'm bringing to the conference is a piece of complementary info on a parallel topic, which is non-orientable for manifolds. I think the title is very self-explaining, but just to get the exposition back on track, let me be more clear about my intentions. I will try to discuss a construction mechanism that works for both orientable and non-orientable for manifolds. A produce of that mechanism is the construction of new examples of exotic four manifolds. So basically, the goal is to construct new examples of four manifolds. So that I start calming down, let me explain my motivation. So I'm going to really start from the basics. Inanch told us about this dichotomy, where if you handed four manifold, you have these two options, where either it has no smooth structures, or it has infinitely many. And there's a myriad of such examples. I would like to place the thought of your mind to be a little bit more humble about that approach, and just say that you picked your favorite four manifold, and you ask, is there an exotic copy of it? Meaning a manifold that's homeomorphic, but not diffeomorphic. Now, let me explain how one way that a lot of people approach this question. So the first is you pick your favorite four manifold. This is already non-trivial because, as you already know, it changes with time, right? You lick your wounds, and then you're like, okay, maybe I'm going to try another one. The second is to construct the exotic candidate. Has, can I call you Sultan? As Andres, Sultan, and Inanch already told us, there are different, very involved ways of constructing such a candidate. So this is not to be taken for granted. Then you use some major results to show that what you have constructed is actually homeomorphic, so you didn't change the homomorphism type. And then you use some other major machinery to conclude that they're indeed exotic, because they won't be diffeomorphic, right? So what I would like to discuss today is Bai's work on how to approach the second step, and how, being very naive about it, you deal with 3 and 4 as well. I hope that becomes clear in a second. So let me start by expressing what we want to do in the way of expressing what we won't be doing. I don't know if that's clear, right? So we learned a lot about Torres surgeries and generalized fiber sums in this conference. One thing that it's always in my mind when everybody talks about this is how cumbersome codimension 2 pi1 computations are. People that were raising dimension 3 from knot theory, I wasn't, I was raising 4 dimensions, are aware of this. So for example, you have a surface inside a 4 manifold, and you want to do something to it. When you take it out, you will add generators to the fundamental group. If I try to make the talk as example-driven and also make the most that there's so many young people in the audience. So take T4, for example. Think about it as T2 times T2. This has free abelian group of rank 4. Remove one of the coordinate tori. And what you get is a puncture torus times T2, right? And the fundamental group of this kid is non-abelian. So this is really challenging. I learned a lot from once Baikor introduced me to this topic. I learned a lot from the work of these authors. I still pretend I know how to use Cypher van Kampen, but most of what I've learned from these people. So I'm not trying to be like, like name dropping or accommodating. If I was a young mathematician, I wish somebody would have said this to me. So that's what I try to cooperate. So speaking about licking your wounds, so we're going to avoid codimension 2 surgeries, right? We're going to go to codimension 1. If you're already in your mind Cyber-Witten or whatever other invariant, we are going to avoid also codimension 0 because of the obvious reasons, if you may. But we're going to be working codimension 3. Are there any questions? Feel free to interrupt me. All right. The second wonderful thing that I've learned from several people sitting in the audience in the recent 2 years, are these involutions on 4 manifolds. I'm very delusional myself, so once somebody told me that K3 has an involution that gives you Enriquez, I thought like, oh sure, involutions are okay, whatever. No, whatever. Like from what we learned from, I'm gonna keep repeating the same name, sorry, Inanj, Sultan, you said it was okay, are that once you have a construction of your manifold, then you can find these involutions which are extremely elegant, but I mean, look at the effort that Inanj and Hamada put into constructing those manifolds, right? So that you get the involution. So in some sense, it's also, you're dragging the cumbersome situation of the codimension 2 gluings. Most of what we're discussing with you today is, we have had a lot of good times, Bais and myself, studying papers from people in this audience. These are the authors. I hope you have had the chance to speak to many of them. I unfortunately haven't. But basically, we're building heavily on these exotic involutions, so to speak. Now, the second recalibration of what we do not want to do is we're going to, Bais is outstanding. I'm not. So if you cannot build involution on the universal cover, just build something downstairs that will give you the involution by default, so to speak, so a posteriori. Do some cut and paste surgery, codimension 3 downstairs, and you bring it up. This idea is not new. This already appears in the paper that Inanj told us about yesterday. I put this in here because I'm still not sure how different these constructions are. What I know is that if you look at it from our perspective, you are able to squeeze some information about the homomorphism type, but it might well be that the manifolds are all diffeomorphic. Sorry. All right, so here's the mechanism. The first thing we want to do, let me draw a picture. So our goal is to construct exotic clothes for manifolds. So the first thing we have to do, since we're doing codimension 3, is the initial data. We already need some raw materials that we're going to go get from the literature. Basically for this talk, the 4 papers that I just presented in the previous slide. So I'm going to get a close for manifold. This is supposed to be this dadaistic for manifold. I want to create something compact with boundary. So I'm going to find a loop, which is the red line, a simple loop. I'm going to remove a tubular neighborhood that for this talk is going to be this piece. And I'm going to throw it away. So I start with something closed. I'm creating a boundary, getting something compact out of it, rather simple. So I'm going to erase that. So now we have a boundary, and I have to shower later. So here at this point, I'm not assuming anything from orientation. So here's 2 choices. If the loop I just removed is orientation preserving, so if the orientation character of the loop is orientation preserving, then the tubular neighborhood is just the product. And then the boundary of that is going to be an S1 times S2. If I have orientation reversing, this is supposed to be the orientation character, then the tubular neighborhood, here I'm taking the opportunity to introduce some notation, is going to be the twisted D3 bundle over S1. So this is a non-orientable manifold, and this is the orientation 2 cover. So it can be something cute like this. First step is pretty much natural. All right. So from something compact that now is X naught, we need to build something close. So I'm going to construct something to cap off the boundary that I just created. Sorry. I'm going to go a little bit faster because, yep. All right. So we need to glue back in something different than this, otherwise I'm wasting your time and mine. What we're going to do is build something that has the same homology. Think of rational blowdown, for example. I think if you put that in your mind, it's simpler to relate. So we're going to build something that has the rational homology of these two kits accordingly. These are very not canonical to build, and I'm going to explain it now. So let's talk about the orientable case. Take S1 times S3. You take the loop that generates the infinite cyclic factor and go around it p times, and then take it out, right? It has also appeared in Ange and Andres' lectures. What you're looking at this handled body right here is a picture of a rational homology force sphere. Well, in this case, it's 2. I'm not going to lie to you. Now, this handle body tells you that you have a 2-sphere with trivial normal bundle, right? So surger it. And that's your SP. To see that you get something out back, you can also just do surgery on that generator. And you can check that this is indeed you have this decomposition. There's some framing issues that I'm not going to worry about, and I'm going to sweep under the rug. Younes Beniaya and Oliviero Malek are in the audience, and they are much more equipped to answer questions about framings than I am. So I can still not pronounce your last name. I'm sorry. All right. So this is the first thing, our contribution that we have, right? So we're being very naive. Let's see, well, what can we get? And it turns out that these pieces that we're building have this magnificent property, meaning that, so for example, in the orientable case, any self-diffeomorphism of S1 times S2 extends to this manifold. That's pretty sweet, right? I'm not going to say anything about the proof, but basically we have complete control of the diffeotropy group of those two manifolds, the Gluck twist, if you may, and we know we were able to extend it to the whole compact manifold. This is an extension of the Laudenbach-Poinarou theorem that allows us to use Kirby calculus and don't draw 3 handles. Work of César Dessat and Maggie Miller and Patrick Naylor recently on the non-orientable scenario. Are there questions? All right. Thank you for the participation. I appreciate it. All right. So the third step of the mechanism is we're going to assemble the manifolds, basically. So get something close out of this construction. I'm just going to set some notation for the moment. I hope it's not confusing that I'm putting a lot of weight into the xi's. I have it pinned down if I want something orientable or not. But now we have new manifolds, which I denote by yi, and depend on the parameter p. Oh, sorry. So here's something important, right? For the orientable case, there's no assumption so far on p. For the non-orientable one, if I do the same construction and I go an even number of times around the generator, I get something orientable. So in this case, p has to be odd, because I want to glue something non-orientable, right? So now, from this construction, I hope you can see, again, this is the one part where I can use Cipher van Kampen and actually don't double guess myself, that at least we introduce fundamental group. So we are building, maybe they're different for manifolds, if you may. All right. The simplicity and of our naivete, if you may, is that these constructions, are so simple that you can actually compute the topological invariance. As Inanj was telling us, once you have fundamental group, like we're spoiled with Friedman, right? You compute the other characteristics, the signature, and the parallel intersection form, and you have this result that tells you have something homomorphic. I mean, that always blows my mind. As Inanj told us, even when you have fundamental group of order 2, the homeomorphism types split in 3 cases. When you have to take care of more subtle invariants, like the second Stiefel-Whitney class of your manifold and the universal cover. So this construction is so simple that you can actually sink your teeth into any invariant you need. More importantly, or more generally, given the theorem that I just presented that extends the Laudenbach-Poinarou and Maggie's and Patrick's theorem, you actually get a homomorphism of the manifolds under some mild conditions. I can discuss them afterwards if you are interested. So we skipped in the procedure to construct exotic manifolds, we skipped the third step, so to speak. Here comes the crux of the efficiency of the procedure, right? It's all fun and games until you have to come up with a computation of a basic class with Sabo in the audience. So what we did is, again, we were having a lot of fun with these papers that we were studying, and we worked out what I consider, I think Bice agrees with me, are the simplest of cases, where we studied Lisa's paper with her co-authors, and we showed, we're really piggyback writing what they did, showing that since their invariant is non-trivial with their constructions, and the simplicity of our construction will imply that it's also non-trivial. Using the paper that Inanj told us about, and then also another very cool paper of Arabadji and Morgan. What Inanj was explaining to us is like these manifolds downstairs won't have an almost complex structure, so there's no monopoles nor not anything. But virtually we can distinguish them using, verbatim, doing what they did. These two, of course, are for orientable manifolds. The fourth step in the non-orientable case is, again, appealing to the simplicity of the construction, is that we have cobordisms available between our manifolds. So whatever invariant is sensible to cobordisms, like, we're good to go. And that's the case of the non-orientable realm. In order to do so, if I may steal 3 minutes of your time in that technical lemma, which I think I can connect with people in the audience, this procedure, and this is also that I'm not sure if this is not exactly what Baikur, Stipchitz, and Sabo are doing. We have control of what we're building downstairs and also to degree 2 coverings. At this point, we need to assume that the P is even. No, odd, sorry. For some very technical, for some heavy reason, we cannot do the even case. And using this decomposition, so again, recall the scenario. We are borrowing these involutions on simply connected manifolds. You get something downstairs that has C2 has pi 1. We glue in our blocks, and what we have control is of the 2 cover degree, provided P is odd. Now, for that lemma to work, the proof is, again, this decomposition of the rational homology sphere, and more importantly, is in this construction of this compact manifold, when P is odd, then in the oriented case, SP covers itself. So we're really just, if you go upstairs, for example, you glue any loop are all isotopic because they're trivial in homotopy, so you will be getting a connected sum with a rational homology sphere. All right. Now, I made it to the end. I'm still unsure how much time do I still have. 5 minutes? Oh, we're good. Thanks so much. All right, so the sample of the produce, and this is where I go into the non-orientable part of the story completely. And this is the theorem that gives the name to the talk today. Is, again, also motivated by what Inanch and Andras and Sultan did. When I was studying that paper, and you build this fake complex projective planes, I said, hey, what about the RP4? I've been a fan of RP4 for a while. And this is what came out of that. So we built two manifolds. This already is an extension, meaning that there was no such examples, even with the standard smooth structure. We have a homomorphism, if I may advertise it. We have homomorphism criteria by Tagner, Hamilton, Craig, all these wonderful people. In a non-orientable case, we only have homomorphism criteria for the C2 fundamental group case. So there's a lot of work to be done. So we really need that theorem in the fourth slide to conclude that they're homomorphic, because it's not as simple as we can put some invariants and then we appeal to a criteria. No. All right. The universal covers are diffeomorphic. This is also well known back from Capel-Shainson. I'll repeat their name in a minute. The point that I'm trying to make there is that we have so much control on what happens upstairs that you can also just go all the way up and understand the smooth structure in the universal cover. This, again, is nothing new. Back in the day, these Capel-Shainson spheres, they were trying to build an exotic S4. They couldn't, and then they have an exotic involution where the quotient RP4 is indeed exotic. These manifolds remain diffeomorphic when you take connected sums of S2 times S2, and they stabilize with a connect sum of CP2. The reason why I'm bringing this point 3 and 4 is basically, again, the simplicity of the construction allows us to understand what properties that our raw materials have from the beginning and the properties that our manifolds will have. And that's where I'll stop. Yes, please.
So I'm not seeing it on the board. So Y1 and Y2 are non-diffeomorphic without stabilization either, right?
I was planning to run out of time. I didn't pay him to ask that question. Thank you so much. So basically, the answer is in your third question. Again, sorry, I'm repeating myself. Besides being nervous, I cannot emphasize it enough. The construction is so simple that you have control of the cobordisms. So these manifolds are non-orientable. They don't have a spin structure, but they have, I don't want to say second best, but second best, what's a pin plus structure. And the connected sums of S2 times S2 are the zero in that bordism group. So since they already started being different in elements in the bordism group, they just stay different on their connected sums. Oh, thank you for your attention. Oh, sure.
Did you say that there was, like, maybe I misunderstood, did you say that the topological, like, classification in the non-orientable case, like, we only have it for Z2? Is that what, did I misunderstand?
What I can, feel free to correct me if I'm saying something stupid. To be more precise, the only theorem I know that you give me a list of invariants, Euler characteristic, ARF invariant, Kirby-Sirian invariant, and then I give you one precise manifold, it only works for C2 fundamental group in the non-orientable case.
Yeah, okay.
And that's due to Hamilton, Craig, and Tagner.
But your construction is for Z to B for an image.
Yes. But no. But only for no. Wait, I appreciate those. But only for those manifolds we build.
Right.
Okay.
Yeah, so you had to, like, your paper, like, has that argument, like, a separate.
Yes.
You have to show homology.
Yes, definitely.
What is the second dimension?
This is Frulan. If Vidusi sees this talk, he's going to smile. This is Frulan. This is a language from a region nearby, and it means get well soon. I hope. Yes. Yes, thank you for asking. I was missing out. We are, like, the first step is get some raw materials.
Can you repeat the questions?
Sultan asked that back in the day, there were already known exotic examples of RP4, manifolds that are homomorphic but not diffeomorphic to RP4. And he asked, what's the relation with our examples? Basically, the way you prove this theorem is you plug in as raw material their examples, the ones you're asking about, and that produces, under this mechanism, our examples. So again, we're really hitching a piggyback ride, in this case, from Capel-Scheinsen. The only contribution is that we add pi 1.
So your examples are essentially different from the known ones because the universe of Hubble is different or something, right?
Yes.
So it's
Yes.
Uh-huh.
Yes, yes.
Yeah.
Thank you so much.